Good day, sir. Good day, sir. This is Adeze Onwuchekwa. This is my term paper presentation on IoT devices for remote monitoring of environmental pollutants in air and water. This is the abstract. So, the abstract is a summary of what this paper is about. So, it examines the IoT-based environmental monitoring of air and water in real time using interface connectedness of sensors, physical objects, chemical materials as things which are placed on infrastructures to be monitored. So infrastructure, so it could be air, it could be the water. So what you do for air, you could actually put some of these, especially if you're using maybe wireless sensor networks, you can actually place the devices on either the rooftop of a house or an industry or the wall of a house, wherever it is that you. The other ones, which is the water, you can use the particular selective electrode and insert in the water body. So these pollutants for air are particulate matters, toxic gaseous pollutants like carbon monoxide, sulfur oxide, nitrogen oxide, volatile organic compounds. For the water pollutants, you have heavy metals, you have dissolved oxygen, estrogens, phosphate, and all of those things. This is a pictorial representation by Liu and other researchers. They came up with this idea that they constructed this sensor. This is an electrochemical sensor that was constructed. I was using application of detection of heavy metals in tap water. They use tap water and lake water as their sampling source. So what happens here is this graphene oxide actually is a substrate surface which absorbs the metal, any metal at all, if it's in the sample, and there's a transmission to this estrogen aerogels. These aerogels are more like what's assisting cation exchange using this ammonia. This ammonia acts more like an electrode. So you see, when we talked about electrochemical sensors in advanced chemical analysis, we talked about limits of detection, we talked about linearity and all of that. So any which metal is absorbed on this surface either undergoes two processes, chemical processes, oxidation and reduction. So what happens is there's also a reduction in this electrode where there's either the limit of detection of either copper or mercury, depending on the metal to be detected, is seen. This is how it displays. When after the oxidation reaction, this is what happened. You see four metals being detected using this electrochemical MOF sensors, and it's so that we should know that these electrochemical sensors are very, very important. They are like the new trend. Why? Because of their selectivity characteristics. That means they can detect as multiple heavy metals or pollutants as possible. So the introduction here will talk on what this air pollution is about, their effects on humans when it is being inhaled. It causes deaths from lung cancer, from stroke, and all of that. You have water too, which when some of these effluent waste, agricultural waste and all of those is discharged into the aquifers of groundwater and directly to surface water, when drank by humans, can actually cause dysentery, pneumonia, all of those things, which is very, very, very deadly. So this Internet of Things system is designed to monitor remotely these pollutants in real time in order to save the environment from devastating effect of these pollutants. Now we have the literature review, which will talk about the IoT being a smart environmental monitoring device, which uses application of specific softwares. The one that is much prominent in this study is the Arduino UNO, which is one of the prominent softwares. They just undergo this. There's this connection, which is more or less like hardware connections, software connections in smart detection of some of these pollutants. For example, if you are using this IoT in physiochemical characteristics of water, that's DO, pH, temperature detection, the global system for mobile communication is used to transmit whatever measurement of data connected with the Arduino UNO software in order to detect some of these materials. This is actually a network architecture representation of what this system looks like. So you have this side, this left hand side, which is the sensor nodes, sensor areas. You have this sync side, which is the right hand side. So all these sensor nodes are connected. They have electrodes that are connected, specific electrodes that are connected to them in order to detect whatever pollutant you are looking for. And the signal, which is a wide area network, is usually used to transmit whatever information to a base station, depending on where the monitoring is being sensed. Where you are sensing, the where you are monitoring the pollutant from, which is the base station. Now, whatever the sense, either from this, which could act as a reference cell, and the sensitive system, you could actually get a feedback of data, what data you're looking for on a web server. It could be a phone, it could be your laptop or your computer, whatever. So there was this argument at some point where this argument stated that how effective is even this Arduino software, how effective is this IoT device compared to the traditional method of detecting pollutants. For example, as environmentalists, when you go for field studies, maybe an EIA, you go for environmental impact assessment or audits, you use some certain equipment like this HORIBA probe in just in situ analysis of the basic physicochemical characteristics of water, pH, temperature, DO, all of those things, even TDS, turbidity, all of that. So when they carried out an analysis on the measurement of the DO in a particular water sample, using these sensors, these IoT sensors, and the HORIBA probe, which is a traditional method, they found out that actually the sensor is actually very effective because they had just slight differences. The HORIBA had and the sensor, the differences in the pH of the stations that were sampled, had the results came out having low differences, which showed that it was effective. You have trends in environmental sensing and application. Here we'll talk about nanozymes. Nanozymes are advanced nanomaterials which have better structural stability than natural enzymes. So what this thing do basically is they detect heavy metal ions in water and soil, pesticides and other organic pollutants in real time. And while it's an advanced method, is a trend, is an innovative trend, is that it's faster in real time in analyzing or detecting or sensing any pollutants than natural enzymes, but they imitate or they mimic natural enzymes. They imitate natural enzymes in this form. So this is the 4 types of these nanozymes. We have the type 1, which includes the iron oxide, manganese oxide. We have the type 2, which is silver, gold, platinum, and all of that. We have the 3D structural mimic and the nano composites. Now, it is noteworthy to state that all of these nanozymes, they are all interconnected in whatever sampling or sensing that you want to do in the environment. So they actually act more as substrates. They act as substrates because of their catalytic activity, depending on their catalytic activity. For instance, if you want to detect mercury in water, if you're using a platinum nanoparticle, which is a nanocomposite, is acting based on its catalytic activity. So what's the activity is going to show you that you will note that, oh, this is actually there's presence of mercury in this water sample, is that it inhibits phenylenediamine and enhances 3,3,5,5 tetramethyl benzidine in the presence of a gold nanoparticle. So you see, from these types, you see that all of these nanozymes are just linked together. So you have this type 2 working together with the type 1 as substrates, where some of these things, these metals can actually be absorbed on. This is a typical chemical reaction representing this. This indicates that, okay, this process will not automatically detect ammonia. If you see the reaction, there's no, will not detect mercury. If you see the reaction, there is no mercury detected. But in this one, you see that ammonia, just once it attaches to this gold surface, inhibiting this and all of that in the presence of a peroxidase oxidase as an enzyme. You remember, it mimics these enzymes. Automatically, you see that there is a detection of mercury. This is what it shows. There's a detection of mercury. You have application of IoT in environmental monitoring of air pollutants, which is going to be discussed soon. IoT device in environmental monitoring of air pollutants. So in this, the smart monitoring system, it will use a request and responder protocol with a combination of address and data-centric protocols to transmit sensor data wirelessly, which is now displayed in a reading system. So it's just typically the way it would for the air pollution is different somehow from the for water pollution, because you see probably its application in special concentration of dust emission, where it uses this LIDAR and MGS tool to investigate the changing process of particles. So this is the processes, the contribution to the absence of quality to transportation and floods estimation of particle concentration. So it basically estimates what is the particle concentration, especially when you're talking about particulate matter. What is the rate at which it is present, what's the rate at which it's, what's the transport system, the floods density and all of that. This is what it is for in water quality monitoring, which we'd already discussed. This one makes use basically of chemical materials, which we already said, and majorly if you are looking to detect or measure the basic physiochemical parameters in water, you use this device. You have to subjugate it to an Arduino microcontroller attached with an electrode, and your result is there. This is the application process for water source. For instance, we know we have two water sources. We have the surface water and the groundwater. So this is what it does. This is a source. This is a collection method. For instance, you go for in situ analysis. You are looking for your pH, you're looking for temperature, you're looking for TDS or DO, depending on which one you're looking for. It transmits, these sensors are connected with an electrode which transmits data analogically to a digital converter. So you use this, the device has actually, it's like you using an electrode. An electrode is analog. You can't automatically get any answer from it. So you have to transmit it to a digital converter, which now takes it to the data analysis. This is where everything is being analyzed. The data is being analyzed. It goes through an internet gateway, stores the data. It's more or less like when you're using a GC for analysis. What basically it does is that it helps you access basic data that you need, store, the normal analysis, the normal advanced sampling. This is how the result comes out if you are doing for basic parameters. This is for pH, this is the calibration of the result. So in conclusion, the recommendation is that a conjugation of these softwares, especially the Arduino, the wide area network and all of that, should be connected to chemical materials, like the nano enzymes, the electrochemical sensors, for faster deduction of results. So in conclusion, we believe that this new system is more efficient than maybe the AAS, GC and all of that, because of its cost effectiveness, especially if you're using chemical materials and all of that. Thank you.